Okay, what? I'd like to introduce everybody to Daniel Alpay, and he is going to talk about quaternions and reproducing kernel spaces. So take it away, Daniel. Thank you.
So thank you very much. I thank the organizers for inviting me to this session, and in particular finally to be there in person. I will try not to use a mic. If you cannot hear me, just let me know that I will use a mic, of course. So this is the title of the talk, and sorry, and so the outline of the talk will be like this. Half of the talk will be really complex analysis to kind of give a motivation on the problems I would like to consider. These are the three first bullets here, and then I will explain why one can go to hyper-complex analysis and to a quaternion setting, why from two points of view, why technically and why it will be of interest. And then if time allows, I will give some examples in the quaternion setting. So this is really the idea, to present a number of problems in complex analysis, explain why it works, why one can extend it hypercomplex, and examples. I would like to mention that there are quite a number, there are a lot of other possibilities which I will not mention, like Grassmann algebra, Clifford algebra, and the like. Here I will focus really on quaternions and two kinds of analyticity. Now, an important point, is the following. Here I want two highlights, in the following sense. I will insist more later on this, but why things work is basically because the spectral theorem holds for Hermitian quaternionic matrices. If you have an Hermitian matrix which is quaternionic, you can diagonalize it with diagonal river entries. This is a very important point. Without this, one can do things, but it would be much more complicated. And one has, this is already a result of Quater of 36, that we will have, in fact, as you will see, in the applications, three non-commuting variables. So it's non-commuted in theory, but which are analytic. So there is a mixture of analyticity and non-commutativity, which is quite unique to this kind of topic, and this really originates with Quater. So let me begin with the first definition, so positive definite functions. I would like to say that the word definite is misleading because there is nothing definite here. These are not strict inequalities, but this is the accepted terminology, so I will stick to it. So you have a function or a kernel, if you want. It will be called positive definite if all these terms which you can see on the slides are non-negative, and equivalently, if all these matrices are non-negative. These are Hermitian matrices, and they should be non-negative. These are a lot of matrices to check, and we'll see later a better way to see whether a function is positive definite or not. So I would like to mention that since these matrices are Hermitian, one could also speak of the notion of negative squares and speak of kernels which have a finite number of negative squares, requiring all these matrices, whatever their size, to have at most, let's say, a certain number of negative squares. This is a result, a notion of Klein in the 30s of the previous century, not the 40s, a notion which is also of interest. And so this, if we want some example, first important example of a positive definite function, so I mentioned here Bortner's theorem, saying that really, if you have a function f(y), it will be non-negative if and only if it is the Fourier transform of a positive measure. And to see some more application of this result, here are two classical examples where you can see that these functions here are positive definite non-real line, and the Gaussian also. We have classical examples just to illustrate what is going on. Now, this is for positive matrices, positive definite functions, and there is the notion of Robertson kernel space. So what is a Robertson kernel Hilbert space? It is a Hilbert space of functions. I insist functions, non-equivalence classes of functions or something, on a set omega, for which the point evaluations are bounded. By Riesz theorem there are a lot of Riesz theorems, but the Riesz theorem for functionals in Hilbert space, it can be represented as a inner product. And the representer here, K, is well, is a function of two variables because it depends on C, and it's positive definite, and there is a very important result that there is a one-to-one correspondence between positive definite functions and proportional kernel inverse spaces. And in this lecture, I will really focus only on Hilbert space, but you could extend these two functions with negative squares and Quaternion spaces. Basically, a Quaternion space, you take a Hilbert space, and a finite dimensional Hilbert space, you take a direct sum and put a minus. And also there is an interesting and important result of Schwarz from 64, that you have a non-to-one, not one-to-one correspondence between difference of positive definite functions and proportional prime space, where here you take two Hilbert spaces, direct sum to the minus between the inner products. So, but here I focus really on the positive case. Another important characterization, an easier characterization of positive definite function is as follows. A function will be positive definite if and only if it is factorizable, meaning you can write it at such an inner product here, where h of z, hz is a function from omega in some Hilbert space H. And what is interesting here is some links with machine learning and support vector machines. When z is in Rn, then it's called a feature vector, and hz is kind of an embedding in a larger space where you can make some separation of data, but all the computations are done in terms of a kernel, so it's much easier than just having a much larger vector h. So this is just a link with another topic of machine learning, so the kernels appear a lot in that topic. So another topic where positive, and all these which I'm mentioning, I will give another example a bit later. The idea is to try to see what happens in the quaternion setting, as I will make clear a bit later. So stochastic processes, there is a result of Michel-Löw, and there is a one-to-one correspondence between covariance of Gaussian-centered processes and positive definite function. And here I wrote an example which is of interest from 2 points of view. The first point of view is, you see, you look at this function, absolute value of 2h plus absolute value of s to 2h minus t minus h over 2h. It's not clear at all that this function should be positive definite on the real line. Here I wrote a representation of this function as an inner product and as a factorization, and from there you can get it. But it's really a trick. But it's not always easy to see if a function is positive definite. But I put this example also because it's of interest. It's the covariance function of the fractional Brownian motion, so which is also a stochastic process of interest. And so I would like to mention that not every Hilbert space of function is a reporting kernel Hilbert space. The counterexamples, they involve the axiom of choice and the fact that in a Hilbert space, a vector, I mean, even more than in a Hilbert space, but a vector space basis will always be uncountable. Here is a result of Donoghu-Mazany, which is related, but I will not mention it. So, a space I wanted to mention quickly before I go to the Quaternion setting is the Bargmann-Fock-Seeger space. As an example of an important proportional kernel Hilbert space, which would like maybe some counterparts in the Quaternion setting. So, this is a space of entire functions for which this integral is finite. So, if you want, this is a geometric representation. It has a proportional kernel exponent omega bar. And it has also an analytic representation, in terms of its Taylor, coefficients of its Taylor series at the origin. And more importantly, and that was proved by Fock and later also by Bargmann, it is basically the unique space of entire functions for which adjoint of differentiation is multiplication, and this is important in quantum mechanics. I mentioned signal applications specifically to signal processing. You see, So I mentioned really analytic functions, but in signal processing the functions are not analytic, are really L2 function or whatnot. And the Bachmann transform maps unitarily L2, which is the space, if you want, of signals with finite energy onto a Fock space. And it allows to transpose problems into problems of analytic functions. And if we summarize this, you see you get kind of a roadmap when you want to study opposing kernel in burst space, whether in the complex setting or in the quaternion setting. There are a number of questions. I do not claim that one can look at all these points, but this is an important set of points to consider. Well, you have a burst space of functions. The point elevations are bounded. You can characterize the space by a function of two variables, or opposing kernel. It has, not always, it's not always easy to find, but in general, you try to look for geometric and analytic characterizations, and the last 2 points are the more important, really. If there is no motivation for the problem, maybe it's also important, but that, for instance, for Fock space, that would be quantum mechanics and recently signal processing and other places. And in the background, there is a ground soul. I certainly do not claim that for each opposing kernel space you can find, one can answer all these questions, but these are questions which definitely one should look at. There are some other examples, and you will just name dropping, I will not go into it because of the time, but the area subspace in operator theory in several variables and connection with models for several operators is very important. The bottleneck spaces and empty space are very important. This really ends the first part of my talk, where I wanted to present, in a very condensed way, some problems or some notions from complex analysis, which I would like to look in the quaternion setting. And there are really 2 points. So what is analyticity? And that would be an important point. Of course, you could speak of, and you can speak of opposing kernel spaces, not of functions, and functions, but without analyticity. But in this talk, this is what I will focus on, analyticity. So just for a summary, this is the Quaternions, as we all know. Just write them E1, E2, E3, E0 being 1. I will also mention briefly the split Quaternion, which here is they're also of interest. And as we all know, one way to construct the Quaternion from the complex numbers is to look at these matrices, Z1, Z2, minus Z2 bar, Z1 bar, and the split Quaternion you just put instead of a minus, you put a plus. You still have a ring, but you do not have a field structure anymore. But see, one can do things. Okay, so as I mentioned in the second slide, and here it's written in a slightly different way, since we still have, you can speak of Hermitian matrices in the quaternion setting, and there is a spectral theorem, so you can speak of positive matrices, so you can define the notion of opposing kernel, and also the list theorem holds there for quaternion Hilbert spaces, so you can speak about opposing kernel space, and what kind of analyticity will we consider? So there are 2 analyticities I would like to discuss. One which is very old, which dates already to the 30s, as I mentioned. And before I mention it, you recall that for a classical analytic function, you look at the operator delta and delta bar, they factorize the Laplacian. And there is a notion of hyper-analytic function. There is left and right, here things do not commute. But I'm just discussing the left case. You have this operator D. A function will be called left hyperanalytic if it's in the kernel of this operator. And if we debark this other operator, you see that there is a factorization of a Laplacian in R4. So in terms of what does it mean in terms of classical function theory? If you identify the quaternions with C squared, then, and also the function, you see that you get, I was putting backwards here, you see that if you write your function f1 plus e2 f2, you have this kind of Cauchy-Riemann type equations. So every time you have results in the hypercomplex setting, you can also transfer them into interesting results in complex variable. And it's also true also for bicomplex number, not only for the quaternion setting. Now, what is interesting is what doesn't work, of course. The product of two hyperanalytic functions is not hyperanalytic, and the quaternion variable is not hyperanalytic, so these are two strong obstructions. But Freighter introduced in the 30s building blocks, if you want, from which you will build hyperanalytic functions and robots in kernels. Well, he does have robots in kernels, from where you can build robots in kernels. The time will not allow, but here is an easy way, which was given in a paper in JFA in 2005, on how to reobtain the Freighter variables and the series. In any event, the counterpart of the power series in several complex variables are what is here, the zeta nu. These are symmetrized products. Product of two Freighter variables will not be hypercomplex in general, but the symmetrized product will be. And this allows you, and there is some similar for the split quaternions as I mentioned here. And for the product of, when you have power series like this, there is a product for hyperanalytic function. It bears the name Cauchy-Kovalevskaya because it was introduced first by Frank Sorman using the Cauchy-Kovalevskaya theorem from PDEs. But basically, it's really the convolution of coefficients in non-commuting power series. And so when you have this, you can write all the kernel robots in kernels you want using the power series. So here would be the quaternion Apperson space. The idea, these are not so much the slides because but the idea that if you replace the Zn by this power set zeta n and the product by the ck product, then you can get counterparts of all the classical robots-in-kernel spaces. And with differences, because the non-connectivity introduces a number of differences. And you have also the notion of Blaschke factor and so on. When you go to a split quaternion, it is quite similar. Simply, you factorize now this operator, and you have also Freighter variables which were defined not so long ago. But as I mentioned at the beginning of the lecture, the quaternion variable is not hyperholomorphic. It's not in the kernel of this operator. If you allow me to backtrack a bit. Is not in the kernel of, excuse me, I was back, of this operator D. So it's a bit of a problem, and there is a notion of slice holomorphicity, which was introduced by Guilloni and Stupa 10 or 15 years ago. Let me go back to the notion, which is the following. So for slice hyperholomorphic functions, and I will not go into all the details, the quaternion variable is holomorphic in this sense. The word slice means what you think. For each time you pick up a unit of quaternions, and you get a number of planes, and you want holomorphicity or classical analyticity in each of these planes. There are interesting problems, and this is really this slide. There is interesting problem with the spectrum. The spectrum is quite not so easy to discuss, but I will not go into these details. These are not details, but in these problems, I will not go into them. Just I want to say that with this power series, you can define also all the classical space. This is only one variable here now. It's not you don't have three non-commuting analytic variables, you have only one. Recently, several counterparts of several variables have been discussed here, but here in this talk it's really only one. And we have branch spaces and everything goes through. And here are some references on the paper. So basically, So, and the split case has been in this paper with Israel Paiva and Daniel Strupa, and the first three are some books on the topics. So, if I want to summarize, there are a lot of very important and interesting problems in complex analysis, and because of the structure of quaternions and the number of basic results for quaternions, you can extend them. It doesn't work exactly the same because of the non-commutativity, but it is an interesting non-commutative theory where we have some analyticity. Both in the slice at holomorphic and the hypercomplex, you have some analyticity, so it is not just a non-commutative theory. And my colleagues from non-commutative theory are always puzzled by this. There is some analyticity and doesn't commute, and it's really an important point here. And as a motivation for this problem, besides the fact that sometimes there are nice results, you can see that in signal processing and in machine learning, people are trying to leave Rn to go to the complex and other sets of numbers, and that would be, let's say, a practical motivation. This is not necessarily my motivation, but I will mention this as a possible motivation. And I see that my time is over, so I will stop and let me answer your questions.
Thank you, Daniel. Are there any questions? Any questions? Okay, we still have a few minutes.
Okay, let's thank our speaker one more time.
Yep.
Thank you.